Okay, thank you all for being here. I'm Konstantinos Plakidas. I'm a PhD student at the University of Vienna. And this is a result of our work with Daniel Schall, our industry partner from Siemens, and my thesis supervisor, Professor Uwe Stone. The title of this is Software Migration and Architecture Evolution with Industrial Platforms, a multi-case study. And it concerns an effort to find a relatively lightweight and as simple as possible way to assist architects in making decisions within the context of architecture evolution and industrial platforms. The motivation is pretty straightforward. We all know that software engineering practice has undergone a very large shift over the last years from monolithic, self-contained and closed systems that are developed within a single organization. We have moved to composite and collaborative systems, where extensive reuse of third-party elements such as libraries or services are is being made, which are provided by platforms and various ecosystems. These elements are reused in whole as black boxes, sometimes proprietary, where we cannot really analyze them for architectural properties, and we must sort of take at face value what they offer us and how they can be included in our system. Furthermore, there is also an organizational separation of development teams and distributed systems, which creates barriers in the communication and hinders the work of an architect in understanding how exactly he is to optimize the composition of a system. Finally, agile practices, continuous integration, continuous deployment, and DevOps require modularity and flexibility to achieve rapid release rates. So this imposes an extra importance on the role of an architect. So, what happens in these environments, in these conditions? The architect is very often faced with too many different, changing and competing offerings, and maintaining overview over this and navigating through the possible options is difficult. During the course of our study with Siemens, we found some solutions that they apparently had not considered, and when we asked them, well, did you consider that? They said no, because we were not aware of that. That was recently introduced into our platform, or this was a solution from a third-party source that we were not aware of. So our aim is to provide just enough architecture, specifically on decisions that are relatively coarse-grained issues, such as services, deployment locations, that change frequently over a life cycle, but most importantly, fundamental constraints, such as legal limitations, the use of specific technologies, the functional requirements of an application that do not change that often. So, in order to provide effective assistance that would actually be used, it must be lightweight, so it should be just enough and not a bundle of documents that no one will read. It should be flexible, which in our view is not following a predetermined solution process with specific steps, but where the architect can choose his own entry point. And it should be extensible, easily modifiable and updatable with further tags and metadata as they are required in any given domain. The key assumptions that we made in creating this model were that we wanted to limit the impact of a decision process, as mentioned, that we wanted to determine the entities and relationships that were involved in taking any possible decision, and to offer useful assistance irrespective of whether the architect was a very experienced one or what his own personal experiences and preferences were. This picture, okay, represents our view of the evolution process, namely that we start with a legacy application which has a pretty clearly defined realization, a set of attributes and a set of constraints. We formulate a number of evolution aims, and the resulting target application would ideally be a mixture of various components. Parts of the previous realization, parts of the attributes, parts of the constraints, including options that are made available through the target environment, through the new production environment that we want to migrate to, and through the possible use of off-the-shelf products. So the method we followed was the grounded theory approach. We made a survey of the existent literature on architectural decisions, on architectural patterns, on a large number of applications, of commercial applications. and we derived from it an initial knowledge domain model, which represents, in essence, the current knowledge of a software architect in terms of what patterns there are, which quality attributes, for instance, a specific application fulfills, what technologies it is compatible with. And we mapped this to a graph-based approach, but this was simply our choice in order to facilitate making queries and finding some solutions very easily. And we tested this model iteratively and refined it step by step through using it in 3 industrial use cases from Siemens. The first one was a migration of an on-premises legacy system into a hybrid cloud deployment. The second was the refactoring of another legacy monolith system into a microservice-based architecture. And the third was a dynamic requirement-based deployment allocation of components of a system between the cloud and the edge. Now, the results of our system, of our approach, do support a flexible approach. We have no prescribed process or decision sequence. You will see an example for this later. An architect is also free to disregard any suggestions that we make or go back when he sees that the choices he has made have led to a dead end. The focus is very strictly on the decision context of a single subtask, of a single evolution step, and we endeavor to limit the number of directly relevant parameters that we display and that are relevant to each decision. The decision option space is limited by matching the various attributes between components and the various model domain sets that we have, by type hierarchies and by versions and variants. More on that will come later. We support a system composition through features and constraints of each component that are then represented in any composite system, and this is scaled up. And placeholders can also be defined with a specific interface. Their concrete implementation can be deferred for later. So in this way, we can ensure both compatibility by design, as well as reuse a third-party application without necessarily being aware of its internal composition. Architectural guidance can be given by using cross-domain links and intra-domain links. For instance, cross-domain here would be linking application types and specific application pattern and specific architectural patterns that these application types support, and through intra-domain links, for instance, patterns that are compatible with each other and that form part of a larger architectural style, such as microservice architecture. We also found, when trying to use this approach, that many of the practitioners preferred to have some sort of reference architecture already given, and we used our model to provide architecture templates for a number of common combinations of patterns, attributes, components, and constraints. Here I give a very brief example. This is one of the legacy systems that we had, very, very simplified view. We have a simple 3-tier architecture, and the various tiers are being realized by a number of internal components. And these components, you can see, lead to the elements that are outside our description, to specific solutions, commercial solutions that realize them. Now, if we want to move part of our legacy application to a new deployment environment, in this case our GIS server, we have taken a choice to replicate a 3-tier architecture there. The links to the previous legacy components still remain, but the GIS server is now deployed in a new platform, and that platform has, among other attributes, a constraint that all off-the-shelf components that are deployed there need to be free open source software. The licenses need to be compatible with that. So step 1, we choose to use the GeoServer, to retain the GeoServer from our legacy system. We know that it is deployed as a service in our target platform. And we are faced with a choice now, what to do with our persistence solution. Because the Oracle database does not have a compatible solution, a compatible license with our new deployment environment. So we can attack this problem through various axes. One axis is simply to say, okay, I have Oracle DB and it is extended through Oracle Spatial and Graph, and this is something that is relevant to data handling of geospatial information systems. Let us have a look what other options there are that provide me the same functionality. Green in this case is indicative of specific functionality. The other option would be to go by type. We know that Oracle database is an object relational database, as is PostgreSQL, and see whether that is a possible solution. If that solution fails, then we can go further up the topology tree to other databases, and so on, and so on, and so on. Now, the ideal solution for this is that the various axes through the topology, for instance, of the applications, through the technologies represented in yellow, through the licenses, or any other non-functional constraints represented in purple, and through the capabilities offered by a specific application or third-party product or service represented in green should match. This would limit the decision space to only a small number of available options. Now, this approach has been tested directly with this model. We are aware of the limitations of it. Of course, generating this knowledge base, populating it, requires a certain overhead, and we can only assume that the data that we can rely on, the documentation of various applications, of previous architecture decisions, is correct and complete. And it is still unclear how the cumulative impact of the individual decision will affect the entire system. So as future steps, we want to refine our model and test it further with more use cases from different domains and with larger scale systems. We want to implement an automated data gathering and knowledge-based population system. And having done that, we want to implement a data-driven machine learning approach to find recurrent solutions, recurrent combinations of the various elements and provide them as an additional recommender to the software architects. Thank you very much. If there are any questions.